Starting now. Let me share a couple of words about you and then this SLS talk. Hello, everyone. Good morning and welcome to this SLS 11th series talk. We are back again after a quite long time. I hope everyone is fine and I wish you a very good health in this very strange pandemic situation. So my name is Sijie. I'm also a PhD student in SCSE. I'm in third year right now. My research area is basically reinforcement learning. So let me welcome one of my very good friends and my lab mate also, Miss Sijie. She has been working for a quite long time in CNCL lab SCSE. She is a final year PhD student under the Professor Molly, and her research interest lies in reliable deep learning. So today she is going to present her work entitled a CLNet, complex input lightweight neural network designed for massive MIMO in short CSI feedback. She had published this paper in WCL 2021. So let me welcome Sijie. Sijie, you are ready?
Yes.
So before she starts this presentation, may I request every one of you to mute yourself. So she will be presenting about 20 to 25 minutes, maybe in between 15 to 20 minutes as well. And after the end of the presentation, you can put forward your questions and she will answer us. Sijie, your slide is already shared, so you can continue your presentation. You can start.
Okay. So, all right, thank you, Manoj, for the introduction, and thank you for the student series talk for inviting me to join the talk. And very good morning, everyone. Thank you for coming today. As introduced, my name is Sijie and a final year PhD. My research interest in exploring reliable deep learning technology and applying them to wireless communication and wireless sensing. So if you happen to have the same interest, don't hesitate to hit me up and we can work together. All right, so today I'm going to present one of my work, CLNet, which was published in IEEE Wireless Communication Letters. The title is Complex Input Lightweight Neural Network for Massive MIMO CSI feedback. The title may sound a bit complicated, but basically this work aims to improve the 5G and above communication systems. And I believe all of us have heard about 5G more or less, and some of your devices may already support 5G. But what's the difference from 4G? Do we actually sense the difference? Today, I'm going to talk about one of the difference, so-called Massive MIMO. So to begin with, I want to, let me show you a data. So as reported, mobility data traffic is growing 47% on average every year. By year 2025, there will be 185 exabyte data traffic, and the mobile subscription will grow up to near 9,000 millions. So this skyrocketing demand requires our communication infrastructures with higher capacity. That's why we need to upgrade our communication system to 5G or even to 6G. And one of the key to achieve the higher capacity is a Massive MIMO technology. So what's a Massive MIMO? As some of you may know, the common LTE communication system, which is cell-based, which means as a user, you will be one of the cells and be served by the base station in that cell. So if the current cell is clouded, or you happens to be the boundary of the two cells, the signal you get will decrease. And Massive MIMO actually makes a revolution from previous cell-based communication system to cell-free, beam-oriented communication paradigm, which means the base station, instead of serve a cell, it will just concentrate the signal energy to a specific user equipment so that it can achieve higher energy, less interference leakage, and hence higher capacitability. So the rationale between Massive MIMO is that by equipping with hundreds, even thousands of antenna in the base station, and the base station can enable the beamforming technology to concentrate the signal energy to a specific user. In order to do so, the user need to send CSI, the channel state information, to the base station beforehand, so-called feedback. The transmission overhead of feedback is quadratically proportional to the number of base stations antenna. So here the logic is the base station needs large number of antenna to do the beamforming, but the beamforming relies on the CSI feedback. The CSI feedback actually, the overhead is very large. It's quadratically proportional to the number of antennas. Therefore, how to feedback CSI accurately and effectively becomes the bottleneck of Massive MIMO technology. And current method based on compressive sensing, which have three drawbacks. The first is it relies on channel sparsity assumption, which cannot hold in reality. And second, to reconstruct CSI in base station requires iteratively computation, which is inefficient. And most importantly, the accuracy is not high enough. So to push the solution be better, recent advanced deep learning tech-based approaches lighten the bottleneck by relaxing the assumption, speeding up the reconstruction, and improving the accuracy. Typically, they use the deep learning encoder, the autoencoder structure, which at the user equipment side, the encoder will compress CSI information, and the base station use the deep learning decoder to reconstruct the CSI based on the received compressed CSI. However, the deep learning based method is still at its early development. Previous work lack of explanation, which prevents further improvement of accuracy. And second, in practice, the user equipment has limited computational resources, so we need to pay attention to computational overhead. And all of the previous work suffer significantly accuracy degradation at a high compression rates. Those limitations direct us to propose a more reasonable and powerful lightweight deep learning solution. So to this end, we propose CLNet with four mainly building blocks that tailored to the CSI feedback problem. The first one is a forge complex valued input layer. So to understand why we need such a layer, we need to first know what's CSI. In other words, what's the input of the neural network. So let's say here have a signal transmit from a base station to a mobile phone that goes through distortion by the in-between stuff. It could be a power loss due to the distance. It could be a power absorbed by the building. And it also could be the reflection and scattering caused the phase rotation. So many factors mixed up together, we call it the wireless channel. Then how the phone will know the original signal should be. CSI is the answer. So a CSI is a complex value channel coefficient whose amplitude, also the norm of real part and imaginary part, give the signal, the total signal attenuation. And the phase is a ratio of the real and the imaginary parts, which describe the phase rotation caused by the channel. And in reality, the channel is much more complicated, not just like how I draw here, only one propagation path. It could be a multiple paths, comes from different direction. So the input actually is a CSI metric, CSI coefficient metric, contains many CSI, denoted as HA here. And each element in HA corresponding to a certain path delay with a certain angle of arrival. So with the information of CSI, the base station can have the idea of how the signal will go through. So it can calculate and doing beamforming to concentrate the signal energy to a specific form beforehand. Keep the physical meaning of CSI in mind. Today's deep learning building blocks mainly designed based on real value. So existing deep learning based wireless communication or wireless sensing system separate real and imaginary parts of the complex value signal to two independent channel of an image input like this, then doing the convolution operation. In such a way, the real and imaginary parts of the same complex value, or I would say the same CSI, are decoupled during the convolution process. For example, here, the 9 complex valued CSI mix to one real value in the first ever process, which may destroy the original physical meaning of each complex value CSI. Therefore, we designed an extra input layer, which utilizes point-wise convolution. First, encode the real and imaginary part together with learnable weights. Mathematically, it was very simple, just like this. But it efficiently preserves the information that the CSI carried, where the ratio between real part and imaginary part is preserved, thus maintain the phase information. And the amplitude of the signal will be scaled by the weight W. Since the convolution operation shares the weights, so the entire CSI matrix amplitude is essentially scaled by the same weight. Thus, the relationship, the relative amplitude across subchannel, or I would say adjacent CSI, is also preserved. And the result output each channel, each small I of the big I is a weighted representation of the original HA. For example, I1 with weight 1 and I2 with weight 2 and so on and so forth. The forge input layer keeps the channel phase information, amplitude information, and also the relationship between adjacent CSI. And then, following the forge complex input layer, we adopt two famous attention blocks, which aims to achieve the lightweight yet information encoder, given the fact that the user equipment, our mobile phone or edge device, have limited computational resources. So recall that the output of our forge input layer is essentially a weighted representation of original HA, right? But among which some of them may be more important than others. So instead of learning it equally, we want to focus on more important part and suppress the unnecessary part. So what we do is to for each small I, we conduct a global average pooling to obtain one statistic valued and many small I together. We can obtain the channel-wise statistic descriptor. We name it Z, which in fact is expanding the network receptive field to the whole CSI matrix. to obtain the global statistical information. Essentially, which this operation can compensating for the shortcoming of insufficient local respective field of previous point-wise convolution, so that the intra-channel relationship being encoded. After that, the Z will go through a transformation, which is a gated layer with activation function that providing nonlinear interaction between channels so that they can encode the inter-channel relationship. Finally, each channel of the big I is scaled by the corresponding attention value of S. Parallelly, we have spatial-wise attention, focuses on learning the place of the more informative part across a spatial domain, based on the fact that the channel coefficient have cluster effect. For example, you can see here and here, they have more information, while above, the white parts don't have much useful information. So we don't want to learn them equally. The spatial-wise attention block first just extract the spatial feature description based on the average pooling and max pooling. The average pooling actually here is to offset for the instability of the max pooling. So we can make the concatenation together and followed by a nonlinear activation and then tying back. By doing spatial attention, we forcing the network to focus more on the distinguishable propagation paths. And to evaluate the proposed module effectiveness, we conduct a ablation study to see the effectiveness of those building blocks. Baseline here means a state-of-the-art CLNet, and we add up with our proposed block separately. Then we use the NMSE, which is normalized the mean squared error in dB scale. Basically, the lower the better. And as a table shown, compared to the baseline here, either we just adopting complex value input layer, or we use attention block can improve the performance, which demonstrate the efficacy of our proposed building blocks. And the combination one actually gives the best result. And besides, we do some steps to further reduce the computational cost, such as we change all the sigmoid function to an analogic sigmoid, which don't have the so-called exponential operation. So it's more hardware friendly. And in the end, we compare the CLNet with a recent advanced deep learning based solution. CLNet, CSI-Net plus here, all based on CNN. And attention CSI here is based on RNN, or more concretely, is based on LSTM. We can see CLNet, the flops means the complexity of the method. So we can see CLNet is the lightest among all the network, and CLNet achieves the best accuracy among those lightweight network. So yeah, that's all for my presentation. Thank you for listening, and I put a paper link and the source code link here. And now I'm willing to take any questions. Thank you.
Yeah, Sijie, thank you so much. That was a very comprehensive presentation from your side, like how the things work, what is the problem, what was initially the problem, and then how did you solve this one, and then finally compare your result with other net technology. That was really wonderful. And we're going to share the paper and code even in the YouTube. Once we complete this presentation, we're going to upload this video into our YouTube channel. We have our YouTube channel. And before receiving the questions, I would also like to share the information that this SLS talk is organized by our club, so-called Graduate Students Club. And if anyone wants to, have a presentation like this, has published a paper and want to give a presentation, want to share the work with us, they can contact us directly. So once again, thank you, Sijie. So let's open the floor and let's receive some of the questions from our audience, from our friends. So who is going to have a first question? Let's see, you can unmute yourself and you can directly ask question to Sijie. Is there anyone?
There's a raised hand from Chan.
Hi, Vijay. Is there anyone?
Is there
Chen Yi Wang.
Hi, hello.
Hi, Chen Yi.
Hi,
you can directly ask the question to yes.
Okay, thank you. So thanks for your presentation, Sijie. I'm the first year PhD from MIMO, so my major is computer vision. So I'm quite interested in your research because I found that your research interest includes reliable deep learning. So actually, I'm also doing works related to deep learning. So I'm curious about, so what's the difference between the reliable deep learning and the deep learning? So are they the same?
All right. It's a good question. Let me clarify it a bit. So for me, because I'm just want to exploring the reliable deep learning to apply it to wireless communication and wireless sensing. So my contents reliable deep learning here is not a research direction in deep learning domain, which could maybe contain the explainable machine learning or so on and so forth. It's more like under my contents, how can I, because we all know the deep learning technology may facing the so-called overfitting problem. So for me, my purpose is to make sure the deep learning technology that I adopt to my research field will be reliable. For example, like this CLNet, firstly, I need to know what a physical meaning of my research and which building blocks can be adopted. And otherwise, for example, I can give another example. For wireless sensing, I also doing work like use wireless signal to do the human fall detection, and also use a wireless signal to do the human identification. Because of wireless signal, as I uploaded before, they'll go through multiple paths. So the situation is changed very quickly. So all the deep learning technology I used, I need to make sure it's reasonable. That's the contents under my description. But I think what you're asking is the specific research direction in deep learning domain. Yeah, that one I'm not an expert, but it's just like, for example, you can give a visualization, or if it can give the explainable, and also it can handle the open set problem. For example, if you do CV like object detection, you have the COCO data set, and you come up with a very good algorithm, and you rank #1 in the data set. But actually, if I give you an open set data set, which just applied in NTU, maybe your deep learning the accuracy will decrease. But for the reliable deep learning or technology, it may also can cope with the open set problem. Yeah. And I know for in our school, the prof Ziwei Liu should be work on that direction. Yeah.
Okay, so I mean, so you mean that the reliable mainly means that the algorithm can solve many problems in practice, right?
Mm-hmm.
For this work, so the reliable, do you need any special design to make it become reliable?
I think the most important one actually is this one, the forge complex value input layer, because the CSI itself is different from the NLP and CV domain. Like it's not a speech, it's not an image. It have its own physical meaning. So we cannot just blindly use popular like filter size, the kernel size equals trees, the convolution operation. It may be very useful in image, but in CSI, it destroy the physical meaning of CSI. And then after that, as long as you destroy the meaning of CSI and you attach more layer, actually you can know you don't have the idea of what the black spot actually do. Yeah.
Okay, thanks.
Okay. Thank you, Qianyi. So there is one message from Chu Xin. Very impressive talk. Thank you very much. I have a small question. Flops may not be linear to the execution time because the memory access time also matters. Would you please talk more about the speed of your CLNet on real world hardware, example CPU, GPU, or DSP? Sijie,
all right.
Please, yeah.
Yes, this actually very, very good questions. Because this research topic is relatively new. It's active from 2019, if I'm not wrong. So all the work currently do is based on simulation. So it's I say this technology not actually adopted by the real communication systems. So some of the researchers may focus on how to do the quantization of the neural network to make it more hardware friendly. For me, that's why for my paper, they don't have such inference time or in specific hardware. Yeah.
Correct. Yeah, that's correct. So yeah, Bijay, please go ahead.
Yeah, I thanks for the wonderful presentation. I was wondering on the data part. So I understand you've used the data set from a previous work, right?
Yes.
So I mean, I just wanted to dig more into that side, like how it has been generated. Is it a real world data set or something else? And can you
No. It's the data set. So maybe I just shared the limitation of this topic. Or I would say if you want to work on this topic, what can you do, right? So as one of the limitations I just mentioned before, so far it's just an simulation. So the deep learning based solution actually haven't been adopted in real communication system. In real communication system, given the faster change of the real communication system, the channel, and maybe some unseen situation, the reliability of the deep learning technology need to be tested. And in addition, most of the paper, also those paper I just listed before, most of the paper in this topic are based on the data, based on only one data set, which just simulation node generated. So we actually use the same data set. It's convenience for us to compare to the performance, but still hope the research community can open source more data set so that we have a better understanding of the proposed method. As in one data set, it have the probability to overfit, right? So yeah, and recently I saw they have some competition based on list, which some research group use a real test bed to collect real channel data. If they're gonna release, then this topic, this research direction will like more interest. Yeah. And also parallel to this topic, like use my paper is use deep learning to do the Massive MIMO CSI feedback specifically, but also you can use in a high level, you can use a deep learning to improve the traditional communication. For example, we can use the non-linearity features of deep learning to design and to design a receiver to make it more robust to noise, or we can make it receive the signal even under the noise flow. That's also a potential research direction. Yeah.
Okay, thanks a lot.
Thanks, Sijie. Vijay, do you have any further question? So then we move to next our next audience. If there is any, please you can unmute yourself and you can directly ask a question to Sijie if you have any. Anyone? It seems there is no one. Sijie, let me thank you once again, and we'll definitely upload this video to our YouTube channel. And let me repeat once again, if there is anyone new to this SLS talk generally is organized by GSC, and if you are interested to share your research work, please you can directly contact us, GSC team, and then we can arrange the talk. Sijie, thank you so much once again, and I think
thank you everyone for coming.
Yeah. Vijay has already shared the email address, SCSE-GSC@e.ntu.edu.ac. So I think Chinese New Year is coming soon, right? So I wish, Sijie, I wish you and to all friends from China very, very happy New Year. And I think when I was in China, they used to say "Kung Chi Fa Cai" or something like that. Yeah, thank you so much, guys.
Yeah, let's reverse it. 恭喜发 paper.
Yeah, that's true. Yeah. So please join us next time. We'll be sharing our next talk very soon. And I wish you once again very happy New Year. Thank you, Sijie. Thank you, Vijay, and thank you, Jenny, and then another friend too for asking questions. And we really enjoy your talk, Sijie. By the way, it was really wonderful presentation from your side. Thank you so much.
Yeah,
thank you everyone, and
have
a great day. Have a good day. Thank you, everyone.
Have a good day. Bye bye.
Bye bye.